The area under each signal in a proton NMR spectrum gives us a sense of the number of protons responsible for that signal. And this is very valuable information. It can help us distinguish between CH3, CH2, and CH groups, for example. And as we'll see in a bit, it can also help us detect symmetry in the molecule when the integrations and the lowest ratios, the lowest whole number ratios of the integrations don't match up with the total number of protons in the molecule that we know from the molecular formula. So this is highly useful information. An integration is often represented with an S-like curve above each signal. What this red curve is showing is essentially a running total of the integration as we move left to right across each signal. And so the height of each of these red curves is a measure of the integration. And they tend to be S-shaped because they start out low, slowly increase over the course of the signal, and then on the other side of the signal, they flatten out again. Now, what the computer program and what the spectrometer does when it calculates integration is just a kind of vague mathematical procedure where it basically does numerical integration across the signal using whatever measure of intensity is internal to the instrument and its computer program. The numbers that you get out of this mathematical process don't tell you the numbers of hydrogens directly. They're going to be pretty much some random numbers that depend, for example, on the exact intensity measure used. But the ratios of these numbers do tell you the ratios of different types of hydrogens in the compound and in its molecular structure. And so what we often will do with these sort of random numbers that are the integrations is divide by the smallest to try to get a sense of the smallest whole number ratios of the integrations to get a sense of how many protons or hydrogens are responsible for each signal. So here, for example, the smallest integration on this spectrum is 27, right here. And if we divide all of these integration values by 27, we end up with basically 1 for this most downfield signal, basically 1.5 here. I'm doing a bit of rounding, but we're going to end up going to whole numbers anyway, so this is fine. Pretty much 1 right here, and pretty much 1.5 right here. Now, to get to whole numbers, we're going to need to scale up these numbers by 2, since these 1.5s are not whole numbers, but can become whole numbers by doubling. And when we do that, we'll see that we have something like 2 hydrogens responsible for this signal, 3 hydrogens for the next one, 2 hydrogens for the one here, and 3 hydrogens for the one here. So I got these numbers again just by doubling these ratios. Now, if the number of hydrogens in the molecular formula is 10, then we know we're done. However, the molecule could have a multiple of this number of hydrogens. 10 is essentially the minimum here, right? It could be 20, 30, or 40, for example, and these ratios could still hold. And in those cases, symmetry comes into play, and we're going to see what that looks like in the ensuing slides. Integrations are relative. This lowest whole number ratio situation for the integrations may not match the actual numbers of distinct hydrogens in the molecule. This comes into play when we have symmetry or distinct, for example, methylene or methyl groups that are chemically equivalent that will overlap and give the same signal and both contribute to the integration for that signal. Let's take as an example this compound, methyl tert-butyl ether. That's this compound right here. The ratio of the integrations for the 2 signals in the proton NMR spectrum of MTBE is 3:1. However, we should notice that 3:1, if this is the total number of hydrogens, that adds up to only 4 hydrogens per molecule, but the molecular formula says there are 12 hydrogens per molecule, and the molecular structure bears this out, right? We have a CH3 group here on the left, that's 3 hydrogens, and we have a tert-butyl group on the right that has 9 hydrogens built into it. So the ratio of the purple to the red hydrogens here is 9:3, which is of course mathematically equivalent to 3:1, but is not equal exactly to 3:1. So here we have chemically equivalent hydrogens contributing to integration and creating a situation where we have a ratio that's a scaled up version of the lowest whole number ratio. And this can get a little tricky if you're interpreting an NMR spectrum, if you don't know what the molecular structure is, and there are things like coupling and chemical shift can come to the rescue. The important point here, though, and one thing that's helpful to review, is that all three of these CH3s are chemically equivalent. That's why they all appear in the same signal, and the integration of that signal is 9 hydrogens. Over here, we've got 3 hydrogens in a methyl group, and we previously said that the 3 hydrogens of a methyl group are all chemically equivalent. So these two appear in the same signal, and the integration of that signal is 3 hydrogens. The ratio of those two integrations is 3 to 1, however. Now, in compounds with symmetry, we see a similar phenomenon going on, where the lowest whole number ratio of the integrations may not match the actual number of hydrogens in the molecule. This happens when symmetry is in play. For example, consider the compound 3-pentanone, C5H10O. If you just look at the integrations of the two signals in the proton NMR of this compound, you get a lowest whole number ratio of 3 to 2. But that only counts for 5 hydrogens, and there are 10 hydrogens in the molecule. We can rationalize this by looking at the molecular structure and saying, okay, I have 2 CH3s on the outside, and those 2 CH3s are chemically equivalent. In fact, they're homotopic. I can turn this molecule over, and that would exchange the 2 CH3 groups via a axis of symmetry, rotational axis of symmetry. So these 2 CH3s are homotopic. They'll give one signal. That's 6 hydrogens associated with these purple hydrogens here. I also have 4 hydrogens in these 2 methylene groups, and like the CH3s, these 2 methylenes are related or exchanged via rotational symmetry, via an axis of rotational symmetry. So the 2 sets of methylenes are homotopic to each other, and all 4 hydrogens would be expected to be at the same chemical shift and part of the same signal, and the integration there is 4. So notice we've recovered our 3 to 2 ratio as a 6 hydrogen to 4 hydrogen ratio in the molecular structure. And this comes from the symmetry. If you only look at 1/2 of the molecule, we see that 3 to 2 ratio. But because of the symmetry, we've got 3 to 2 times 2, essentially 6 hydrogens associated with the 2 methyl groups and 4 hydrogens associated with the 2 symmetrically disposed methylene groups. In this example problem, we're given the molecular formula of our compound of interest of the sample and its proton NMR spectrum along with integrations, and we're asked to determine the number of protons giving rise to each signal. So the first thing I like to do in problems like this, and when I'm considering integrations, is take a look at that molecular formula and note the number of hydrogens that I'm looking for. There should be 10 hydrogens total accounted for in the integrations in the final integration values that I land on for each of these signals. And if I get a number that's, say, smaller than that, say 5 rather than 10, I may need to scale all the integrations up. After noting that, we're going to look for the smallest sort of random integration value from among the random values here in red, and divide all 3 of the integrations by this smallest number. That's 6.33, so we're going to divide each of these by 6.33. The most downfield signal comes out to 1, the one in the middle we end up with 3, and the most upfield signal we end up with an integration of 6. So this is the lowest whole number ratio of the integrations, 1 to 3 to 6. Now at this point, we're going to add up these numbers and see if the sum is equal to the total number of hydrogens we need to account for. If not, we may need to scale, right? And if so, we're happy. And in this case, we're happy because 1 plus 3 plus 6 is 10, and all of our hydrogens are accounted for. So the integration of this signal on the far left is 1, the integration of the middle signal is 3, and the integration of the signal on the right is 6 hydrogens. One thing I'll leave you with, it's a bit of a cliffhanger here, has to do with the number of subpeaks and their relations to the integrations, in particular for this signal and this signal. One thing we notice is that if you really dig in and peek at this 1H signal, in fact, I'm going to zoom way in here, we can count 7 subpeaks within this signal. 1, 2, 3, 4, 5, 6, 7. It's what we'll call in the very near future a septet. And that's one more than the integration of this signal, 6 hydrogens. On the other hand, this signal very clearly has 2 subpeaks there, and this is one more than the integration of this signal. That's actually not a coincidence. These two sets of protons are what we call coupled to each other, and coupling provides us with extremely valuable structural information. From the information I just told you, recognizing the integrations and how they're related to the number of subpeaks, and paying attention to the spacing between those subpeaks, which we'll talk about in the next video, we can infer that the carbon to which this hydrogen is linked to carbons that bear these 6 hydrogens. Most likely 2 methyl groups to account for all 6 of the hydrogens. This is the kind of connectivity information we can get from Proton NMR, and it's what makes it such a powerful analytical technique.